Good morning. We have, let's see, for Monday, we're going to continue on, wait a minute. Okay, today is Monday, and we're going to be talking about Chapter 10. Wednesday is going to be an opportunity for extra credit. We're going to, if you aren't taking off for Thanksgiving early, it will be Trivial Pursuit, Intermediate Physics for Medicine and Biology. And then Friday's no class. And then the next Monday, we will continue on Chapter 10 and really finish up the new material on feedback. And then the rest of the semester, Wednesday and Friday of next week, will be spent reviewing for the final exam. So that's the game plan. You have one homework assignment left. That's homework assignment number 9, which is Chapter 10, and that's due not this Friday, but a week from Friday. And just to remind you, the exam is on Monday, December 9th, so that's 2 weeks from today, so we're getting very close to the end, and that's the game plan. So, what we want to talk today is the last topic in this class is going to be feedback. And we're going to start by looking at one of the homework problems that is not on your assignment. So from the book, problem 10, chapter 10, number 10. And this is about how the body stays cool. And we've talked about mechanisms to stay cool before when we talked about chapter 3. But we're going to look at it in a little more detail this time. First, we're going to look without any sort of feedback, and then we're going to enter in how you can get feedback to maintain your body temperature. So first, without feedback. We talked earlier in the semester about if you have a certain amount of energy per unit time generated in the body, if you don't have any mechanisms to get rid of it, that's going to raise your temperature. And the amount that your temperature goes up is going to be the heat capacity times the rate of time increase, the temperature increase. So basically, the rate of energy increase is C times the rate of temperature increase. And then we also talked about mechanisms that increase and decrease your temperature. And we had one which was just metabolism. And that increases your temperature. And then we had one when we talked about Newton's law of cooling. We said you can lose temperature, and you had some sort of constant K, and then had T minus the surrounding temperature. So the rate of temperature loss or temperature decrease depended on the difference between the body temperature and the surroundings. This is really a convection term. Okay, that's all review. Now, if you want to know what the steady state temperature is, steady state means no time changes with time. So you zero out this, and you get 0 equals m minus k t minus ta. So if we solve that for t, we get t is equal to ta, and then this becomes plus m over k. That's the steady state temperature of the system. And we can also learn something else. We can learn, if it's not the steady state, how fast changes occur with the system. So a time constant. So if you look at this, if you divide this equation through by C, you're going to get the temperature dt equals, well, there's going to be an m over C. And let's look at, put this term over here. This is going to be a minus and a minus, or a plus k over C times Ta. So that's all constants. And then there's going to be a minus k over C times T. Now this really looks like that equation we've solved many times before. The rate of change is equal to a constant minus another constant times the temperature. So do you remember what the time constant, this would give you an exponential type of behavior. What is the time constant tau going to be in this case? Anybody remember that? In general, our equation was something like this. it had some constant, I'll just call a minus t over tau, where tau was the time constant. That's the general form of this. So, because in this case you get an exponential, if you ignore this term, you get an exponential, just e to the minus t over tau. So if you just look at this, if you put the k down in the denominator and the denominator, this should be t over c over k. So the time constant is c over k. The steady state value is Ta plus m over k. And that is really nothing new. That's what we saw for when we were analyzing getting rid of heat. It's really when we analyzed Newton's law of cooling. We were doing something very similar to this. All right, so now what I want to do is I want to put in feedback. And to put in feedback, we have to look at the next problem. 10.11, still not on your homework assignment. And here, we're going to add in one more mechanism to stay cool, and that is sweating. So, you're going to have C dt dt, just like before. Everything looks like before, except now you're going to have to subtract off something called Qs dot. That's really the rate of heat loss from sweating. But now here's where the feedback comes in. The rate of heat loss from sweating depends on the temperature. Your body senses the temperature, its internal temperature, and if this temperature starts getting higher, it begins to sweat. So Qs dot is, well, it's going to have this funny form. If your temperature is below 37 degrees, you're not going to sweat at all. So you get a 0 if the temperature is less than 37 degrees C. But as the temperature gets above 37, you begin to sweat, and you sweat more as you get higher temperature. So you can get L T minus 37 or T greater than 37 degrees C. So that's comma, comma. And what you find now is a continuous function, because right at 37 you get 0. Your temperature begins to increase, and we're going to assume it increases linearly. So now what we want to do is we want to analyze this system. And the first thing we can do is find a new steady state. Well, that's just going to set this equal to 0. But let's just set that equal to 0 and solve for t. And if you do that, you'll find you get Ta, and you get plus m over c like we did before. And you're also going to get a minus Q dot S over C. Why did I divide by K? I think that's right. Over C. That would be your new steady state. But this depends on temperature. So it gets to be a more complicated system. And we're going to have to substitute this in here. But before we do that, I want to, first of all, ask any questions. I want to draw this in as sort of a generic way to represent feedback systems that we're going to be doing. So I'm going to erase this. And let's look at this kind of pictorially. Because oftentimes in the homework or on an exam, I'll ask you to draw sort of a schematic diagram of the feedback system. So here's what we're saying is you have temperature, and it depends on the rate of sweating. And that's really this equation here. The temperature is going to, some constants, it's going to decrease as your sweating increases. And it's linear with a minus sign. So it tends to go down like this. Now we can think of the surrounding temperature as a parameter. And if you change the surrounding temperature, this would be what it is for TA. If you use a different surrounding temperature, it would switch to TA prime, some new value. So you're going to get a straight line, but the actual value of that straight line is going to depend on the surrounding temperatures. So I'm going to put a box on it around this. And what this says is, if I know the value of QS dot, the dependent variable, I will get out a value of the temperature. But then we have a feedback system. Your body senses the temperature. It determines how fast you sweat, how much you sweat. So what the body does is QS dot senses the temperature, and if the temperature is less than 37, you sweat by 0. So you get here. And if the temperature gets more than 37, you begin to sweat linearly up, so it looks something like that. And we're going to put a box around this. And what that says is, if you tell me what the this tells me, okay, if you tell me T, this will give you QS. So that's how the causality works. And then this comes down and feeds back over into here. So you have a big loop. It's a feedback loop. And it says that temperature determines sweating, sweating determines temperature. This is very similar to how your furnace thermostat works. Your furnace turns on and increases your temperature. But the thermostat senses the temperature, and if it sees that your temperature is getting too high, it'll turn off the furnace. So the same thing works here with sweating. Now, what we'd like to know is, what is the set point? What is the temperature that it actually functions at? So to see that, we're going to have to take these two plots and we're going to plot them together. Here is just this plot. Now what I'm going to do is I'm going to take this plot, but the plot is on the same axis. I'm just going to flip it over so that this is now temperature goes up to 37, 0, and then it begins to rise like that. And both of these have to be true, so that means the set point is right there. Set point. So to find the set point, you have to solve these simultaneously. Which means, let's assume for a moment that our temperature is larger than 37, so that we're actually on this branch of the curve. If you're larger than 37, that means this QS dot is going to be M over C minus L T minus 37, and we divided 3 by C. So this becomes our new expression for the temperature, but temperature is here and temperature is over here. So what we can do is we can solve for T. And here we got a minus sign, but we'll bring this term over the other side. So the temperature is going to have 1, that's that term, plus, because that's brought to the other side, L over C equals, my notes keep saying K, and I want to make sure if I have somehow screwed this up. I don't think I have. TA over C, I think I'm good. Equals, what's left? A bunch of constants. TA plus M over C minus, and the minus becomes plus 37L over C. Or in other words, temperature is equal to TA plus M over C plus 37L over C divided by 1 plus L over C. All right, now, let me stop and think for a second, because I think I'm still worried about this C being downstairs when my notes say K. What did I do? Okay, here's the problem. I set the steady state to be 0. So this side is 0, and then I solved for T. I should have divided everything by K. That was my mistake, and I'm going to go through and correct it now. Sorry about that. My notes were right, but my brain this morning was wrong, because I got this from the steady state. In fact, once you set that term to 0, C is no longer even in the equations, which is why it should have been obvious to me. Okay. Now, what we can do is we can look at this. This numerator is the steady state temperature that we got if there was no feedback. So the feedback is all accounted for by this 1 over 1 plus L over K. That's the amount of change you get with the feedback. So let us look now, and
it's still a C on that side.
oh, where? Because I had didn't catch
Sorry,
that. Thank you.
Interrupt.
That's good, because that fixes that too. All right. Now I think I've got this straightened out. Okay, now, what I want to do now is I want to ask ourselves, suppose this temperature, which depends on TA, suppose TA would change all of a sudden. You have a surrounding temperature, say it's reasonable, it's maybe 38 degrees or something, a hot day, but then in the afternoon it gets really hot and it goes up to a higher temperature. How does the temperature of our body change? So that's the question. So I'm going to have to erase the feedback loop here and look at how the temperature of the body changes. All right, so if there's no feedback, so no feedback, you have T, Q, S dot, you have this curve coming down, you have this curve going up, that's your set point. Now, if you change the surrounding temperatures, that changes you to another curve here like this. And if there's no feedback, that means that the amount of sweating doesn't change. So that's our assumption. No feedback means the amount of sweating. You might have some sweating, but if you change your external parameter, your sweating does not increase. That just means you move up to the new point right here. And that's really just the increase. So your temperature is basically going to change and be equal to the change in the temperature of the surroundings. It essentially says if you don't have this denominator, which is a feedback, if you change TA, you change T. They're proportional to each other. So what happens if you have feedback? QS dot T. And you have temperature, and you have this. And if you raise the ambient temperature, you're onto this line. Now, you were at this point, and now you change the outside temperature. What you're going to do is you're going to move up here, but then you're going to sweat more, and it's going to move you back down. You're going to be basically at a new set point where the two curves now cross. So what happens really is, if you look at this little triangle right here, in a little more detail, this is going to be your change in the ambient temperature. That just raises the ambient temperature. And this piece here is really your change in temperature. That is how much does the temperature change. That's what we're really after. And this is going to be your change in QS dot. That's a delta. Change in QS dot because you sweat. And you can write the relationship as your change in temperature is equal to your change in TA plus, well now, how much you change in temperature depends on the slope of this line. Because that, you're going to change your sweating, but really that will translate into temperature. It depends on that slope. So that's going to be your how the temperature changes with QS dot. times your change in QS dot.
For that one above, I'm confused because you have it as just change in TA on the left, but now it's that one on the right.
This curve goes with this plot down here.
Okay.
So yeah, that is a little. Maybe that will help. I'm just running out of space. All right, so we need to know what dt dqs dot is, and that really means we have to go back to this equation where here, and that tells us that dq dt dqs dot is just a minus 1 over k. So we're going to get your change in temperature. Now I'm moving way down to here is equal to delta TA, and you're going to get minus qs dot, your change in qs dot over k. But how much is the change in qs dot? Well, that will depend on this equation. If you change qs dot, you're going to get, think of it as taking a derivative almost. If you make a change in qs dot, that's going to give you a change in your temperature. Actually, this term won't even be there because the change will get rid of that term. L delta T. So essentially what we're finding is dqs dot dt. And so that's going to be equal L. So qs dot will be L delta T. And you get minus L over K delta T. And if you want to then calculate what delta T is, you can find that. And that's going to be delta TA over 1 plus L over K. L over K. And this is your change in temperature. Now, notice what that says. That says the temperature is now going to be smaller. The change in temperature of the body is smaller than the change in the ambient temperature. If you didn't have feedback, you would just have that the change in temperature is equal to the ambient temperature. But with feedback, it gets smaller. So the feedback's a way to try to hold your temperature constant. Let's put in some example numbers. So, let me get some more space here. Okay, typical numbers. L is equal to 750 kilocalories per hour degree C. Now you may think, oh, those are horrible units. Well, the good news is that L and K, when you divide them, it's got to be dimensionless. So as long as L and K are in the same units, it doesn't really matter whether you use some kind of strange units or not. And that means I'll give you K, which is also in those same strange units, kilocalorie per hour degree C. And the ratio, L over K, is what's important. And the ratio L over K can be 30. What that really means is if I had drawn this plot carefully, this slope would be much shallower than that slope. It means that this line comes in and actually looks more like this, up and almost straight across, so that any sort of change is not going to change the temperature much. It'll just change the sweating a lot. And in fact, that means delta T will equal delta TA over 31. So if you raise your temperature by 31 degrees, your body temperature would raise by 1 degree. It's a way, feedback loop, a way to maintain your body temperature as stable as you can. And if you make L bigger and K smaller, you can actually get as stable a temperature as you want. You just have to have the feedback loop have enough response. Okay. We can rewrite this into general terms. This is an example for this particular project. But in general, you'll find that a change in the variable is equal to the change in the variable if there's no feedback divided by 1 minus something called the open loop gain. So in our case, the open loop gain is just going to be minus 30. It's minus because really the slope of one of these curves is negative and the slope is positive. So you get something called the open loop gain. And if you want to write what the open loop gain is in general, it's going to be the change in temperature with respect to QS dot times the change in QS dot with respect to temperature. You have to realize this carries a certain amount of causality to it. This is the equation that gives you your temperature if you know what QS dot is. And this is the equation that tells you how much you sweat, what your QS dot is as a function of temperature. So this is the body regulation part. And if you look back at those original equations, you'll find one of these is 750 and one of them is 30, but one of them is negative. So you get a minus 31 for the open loop, or minus 30, excuse me, minus 30 for the open loop gain in this case. So 1 minus a minus 30 gives you the 31. So in general, when we talk about feedback loops, we'll be talking about their open loop gain, and that's the way you calculate it. All right? Yeah, one more thing I want to mention about this particular example. This is a pretty interesting example. So I'm going to have to get more space and go back to the beginning. We've been talking about the steady state case. But now I want to go back and look at how things change with time. So to do that, I will write C, the temperature with our time is M minus K, T minus TA, and then you had minus QS dot. But QS dot was dependent on temperature. And if we're in that branch where you're sweating, you get a minus, and it is L T minus 37. That was the value for QS dot as a function of temperature. So this is the QS dot term. Well, let's analyze this. First of all, let us divide through by C and write it as dt, temperature, little t. And here's M over C. Here is this term, it's minus and a minus, so it gives you plus K TA over C. Those are all constants. And L and 37, a minus and minus gives you plus L 37 over C. Those are all constant terms. And then there's two terms that depend on temperature. And they're both negative, so I'll write minus, and you get a K over C from this term. So all times the temperature. And this term gives you a L, and that's a minus and a minus, but that minus sign's been taken out. So plus L over C. What's the time constant for this equation? So remember, this is all a big constant. Minus, the dt is minus something times the temperature. That's that same exponential behavior. And you can think of this as being temperature over a time constant. So the time constant is just going to be C over K plus L. And I'm going to write that in a funny way. I'm going to write that as C over K. And I've factored the K out, so this becomes 1 plus L over K. That's seemed like a stupid way to write it, but it turns out it'll be useful. Because this thing up here, C over K, was just the time constant we got with no feedback. So that's tau with no feedback. And this is our 1 plus L over K, which is really 1 minus the open loop gain. So in general, you get that factor of 1 minus the open loop gain, which tends to be very big. So what this says is the time constant is the time constant with no feedback divided by some number, which might be pretty big, which means the time constant itself with feedback is small, which means that systems that have a lot of feedback will tend to go to their set point fairly quickly. Not only does it keep temperature fairly constant, but it makes the changes happen fairly rapidly because you've got the smaller time constant. So, in general, feedback systems. You have some sort of mechanism by which your body senses some parameter and then adjusts either somehow the body adjusts to hold that parameter fairly constant, and also it tends to make the parameter change fairly rapidly. And that's the essence of feedback systems. This is one example of how we stay warm, stay cool, really, regulate our body temperature. Now, if you want to know how we stay warm if it's very cold outside, you're going to have to actually bring in a different feedback systems because that flat part of the curve, the QS curve below 37, means it no longer operates as a feedback system. You can't have negative sweating. You'd have to have other mechanisms like shivering or just putting on clothing, or else you just get cold. And if you are out on a cold day, you'll eventually get cold. So, but this is very insightful for higher temperatures. Okay, that's a classic example of a feedback loop. And what I want to do now is look at a totally different feedback loop. So let's get rid of all this. Your body's just full of feedback loops. So here's a famous one. You can have, how do you control your blood glucose level? Well, let's call G equal your glucose concentration. And I is a hormone, insulin, which your body secretes, your pancreas secretes actually. And the hormone affects your blood glucose. Now your body doesn't want the blood glucose level to get too high. So if it does, there's all sorts of bad things happen, and your body needs to maintain a fairly low blood glucose level. We're also going to have one parameter, R, and this is going to be a parameter that's really the rate of glucose production, usually from metabolism. So if right after a big meal, this might be a large value. If you've been fasting for a long time, this might be a very small value. So let us look now how this feedback system works. You have, like I said, insulin affects your glucose level. So you can write this, and these are equations, and they're approximately right. Usually these models are a little, in reality, more complicated than what I described, but this is approximately right. It's divided by 2 plus I. So, as insulin level increases, the glucose level decreases. But, how does your body know how much insulin to make? Well, it has insulin sensors, and basically, if your blood glucose level starts increasing, it'll increase the amount of insulin. Let's see, let's 400. That's your feedback loop. So that's the insulin produced by the pancreas. This might be, for example, if this is on an exam problem, I would give you these two equations. First thing I want you to do is to draw this like using a schematic diagram showing the feedback loop. So this equation here says if you give me I, you can get what G is. Okay. Well, if I is 0, you get some value of G. But then as I increases, G begins to fall. So you're going to get some curve that looks like this. And that, we're going to put a box around, and that says that if you tell me what I is, the dependent variable, or the independent variable, I will tell you what G is, the dependent variable. But your body senses the insulin. So we now have another curve, which is insulin as a function of G. As G gets really big, if G is a lot bigger than 400, this becomes G over G, which is 1. So it just becomes a constant, 50. So it's eventually going to become a constant. But if G is really small, a lot less than 400, this just looks linear with G. This is going to be coming up linearly and then turning over and becoming a constant. And that says that if you tell me what G is, this equation tells you what I is. And it's a feedback loop, so it comes back and feeds back in. And there's also a parameter R, and sometimes I like to draw that as the R goes into this equation, but not the second one. That'd be how you draw the schematic diagram. Okay, before you eat a meal, R is going to be 0. So let's see what happens when R equals 0, and let's see what the actual blood glucose level and insulin levels are. We have these two equations which have to be true at the same time. So you have G is equal to 1200, and there's no R because R is 0, over 2 plus I, but I is this big mess, 50 G over G plus 400. And you want to know what G is, because you've removed I, and now you solve it for G. Okay, this looks like a big mess, doesn't it? First thing we'll do is, having this thing in the denominator really is annoying, so let's write this as 2 plus 50 G over G plus 400 all times G equals 1200. Right, it was still annoying because you still got this thing in the denominator. So we'll multiply both sides by G plus 400. So that'll give us, okay, this will go away, but that'll give us 2 times G plus 400. So 2G plus 800 plus 50G. I'm just multiplying both sides by G plus 400. So there's the 2G plus 800 plus 50G times, this is all times G, so really the whole thing's times G, so this would be 2G squared. 2 times G plus 400 times G, this would have a G in it, and this would be a G squared. Equals, and now I multiplied the whole thing by G plus 400, so I would get 1200 G plus 1200 times 400. So plus some big number, which is 4 times 12 is 48, 0, 0, 0, 0. And that whole thing, okay, that's equal. Now, 50G squared plus 2G squared is 52G squared plus, there's 800. This is 1200, and I bring it to the other side, it's a minus 1200. 800 minus 1200 is minus 400G. And then there's going to be a minus 480,000 equals 0, and that looks nicer. Because you know how to solve that. That's a quadratic equation. All right, if you solve that, I'm not going to go through the whole thing in detail. But if you do solve it, you're going to, first of all, you're going to find out that somebody made the numbers nice, so that the thing under the square root became a perfect square and it went away. You're going to get two solutions. One's going to be negative, but you can throw away the negative solution because you can't have a negative glucose concentration. And you get one that's a positive solution, and if you calculate it, you get it's 100. So you get G equals 100, and I encourage you to go check that after class. And if G is 100, then what's I? I is 50 times 100 over 500, so that's 1/5 times 50, so I is 10. And there's your set point. So you can find the set point. There's another way you can find the set point is you can just graph these two together on the same axes and do a very careful graph. You can find it. Lots of different ways you can find it. That's the set point when R is 0. Okay, now, we have a big day coming up this week. Thanksgiving. You're all going to be eating a lot of turkey. Hey, yes?
Oh, I'm sorry, just...
And when you eat all that turkey, you're going to start producing all tons of glucose and pouring it into your bloodstream. So your R is going to jump up. So our question now is, how much does your blood glucose change if your R changes? And your R is going to go up now to 2,400. So I'm going to change all this, and I'm going to do it sort of with eraser math here. If you have R now equals 2400, what's that change? That means you got 1200 plus 24, so the whole thing's going to be 36. So this 1200 is going to become 36. Everything else will be the same because it doesn't affect this equation, doesn't affect the denominator. So the whole thing will become the same, except this 1200 will become 36. And you can solve it in the same way. And I'm not going to go through the whole analysis again. It's still a quadratic equation, it's just the numbers change. So this, which was no feedback, or this was R equals 0. Now, you'll find if you do that analysis that you're going to get G equal 196, and I is going to equal 16.4. That's with feedback. So that's R equal 2,400 with feedback. Now suppose I asked you what would have happened if the feedback turned off. What would have happened, and before I do that, let me just say, how I got these numbers is I basically solved this equation, this quadratic equation, just like we did before. The only difference was this number was bigger. I don't want to go through all that again, but you can check it. Now, suppose I asked you what would have happened if your feedback system turned off. Suppose that inside the cranberry sauce was some toxic chemical that ruined your ability to your pancreas to sense blood glucose concentration, so it couldn't change the amount of insulin it's submitting. Well, in that case, I would be fixed at 10. If I was fixed at 10, but R increased to 24, so that would mean no feedback. What would you have is you'd have G is equal to, well, G would still change because this would be 1,200 plus 2,400, 3,600 divided by 12, and that would give you 300. And I, we said, didn't change because this drug ruined your ability to change the amount of insulin. So what you get is this set point. No feedback with feedback. Now, let's ask ourselves, what's the purpose of the feedback? The purpose of the feedback is to keep blood glucose approximately constant. Well, it still went up, almost by a factor of 2, but it would have gone up by a factor of 3. So the feedback loop is working. It's not a feedback loop with a huge gain. So it doesn't maintain your blood glucose real constant, but it does keep it from going up super high. So the system seems to be working. And people who have diabetes don't have either they've lost the ability to produce insulin at all, or they've lost the ability to have the amount of insulin changing and sensing blood glucose and changing, so that this is not just a hypothetical example. It's something that has an impact on people's health. So that's another example of feedback loop. So, any questions? You guys are very quiet today. Let's just look at some of the homework problems now and see what we're going to be doing on homework problems. All right, so I'm going to erase all this and we'll start going through. We've already talked last class about the last 4 homework problems, the ones in the 40s. The ones in the teens are the homework problems with feedback. So, first of all, problem 12. Okay. You have a arterial blood pressure. And the arterial blood pressure, one that has a particular place in the carotid artery, it has a sinus, which is really a place that senses the blood pressure. But it's part of the arterial blood. So you know that in the carotid sinus, you just have the same blood pressure as you have in your arteries in general. It's part of the arterial system. However, the reason you have this carotid sinus is it detects your blood pressure, and then it can change your body, the way your body responds, and it can actually change your blood pressure. So there's a feedback. Your arterial blood pressure is going to be 90 plus 120 over 1 plus e to the p sinus minus 165 over 5. And this is your feedback loop, and you can draw a diagram of the feedback loop. In almost all of these cases, there's some system where your body senses some important parameter and then adjusts a hormone or adjusts some feedback to try to hold that constant. Now, how do you do this? Well, you can just put in for P sinus, you can put in P arterial, and you'd end up getting P artery equals 90 plus 120 over 1 plus e to the P arterial minus 165 over 5. And you have to solve that for the set point. Problem is that you can't solve this analytically for the set point. You could try. You're not going to get a quadratic equation. You're going to get some transcendental equation. Some P arterial is equal to something with an exponential. This is an example where you actually have to solve the thing numerically. You have 2 choices. You can plot these 2 functions. Make a plot of P sinus versus P artery. Very careful plot. One is going to be a straight line, and one is going to have some shape. I don't remember exactly what it looks like, but something like that. And then you can find where this is just by inspecting the plot. And maybe you'll have to replot it with an expanded scale to try to get it as accurate as possible. Or you can do this just by trial and error. You can make a chart and you can say, well, here's a value for P arterial, and then I'll calculate this big thing, 90 plus 120 over blah, blah, blah. And that depends on P arterial. So you put in the value, just pick a value of 50, and you can calculate what this is. Then you put in a different value, and you can see if this gets closer or farther from the actual value. And if you do that, trial and error, after about 10 times, you should be able to get the arterial pressure to a couple of significant figures. So, if you can't solve the equations analytically, you just solve them numerically. You don't have to go and find some fancy Newton's method or anything to try to do this using fancy methods unless you want to. You can either just plotting, trial and error, either one of those will get you there. You only need a couple significant figures. I don't need this set point to 10 significant figures. It's just not that important. So that is problem 12. Okay. If you have trouble with that, remember to bring questions. Probably it'll be next week sometime. You can ask me more detail about how to do it. Okay, problem 16. Problem 16 is how we keep track of our osmolarity. Remember in chapter 5 we talked about how your osmolarity of your blood, how much stuff is in there, how many milliosmoles of stuff is important. Because if it gets out of whack, you're going to have water flowing into or out of your cells. So you have your blood osmolarity, C, and this is controlled. Your body senses the blood osmolarity, and it's controlled by a hormone, an antidiuretic hormone. And what you find is that the antidiuretic hormone basically causes your osmolarity to go down, but your body produces this hormone depending on the concentration, which is going to look something like that. The problem actually gives you equations for these. I'm just drawing pictures. What you're going to do is you're going to solve now for the set point and whatever else the problem asks for. Now this kind of looks similar to the problem we saw before, and these curves are such that this problem you can solve using the quadratic equation again, like we saw in the previous example. So you should be able to get an analytical solution for this and solve it as it asks for. It's just another example of feedback. This is my co-author Russ Hobby likes to say you can never have enough of these examples. So problem 17 is another. If your potassium concentration gets too high, it can be deadly. Potassium can affects. Remember, most of your cells are sitting at the rest potential determined by the potassium nurse potential. So if that drifts up too high, the potassium nurse potential will depolarize, and all your nerves and muscles will stop working. So it's very important that your body maintains the potassium concentration constant. And it does that using a hormone, aldosterone, which we use as A. And you end up getting a feedback loop. K falls with A, and A increases with K. All these negative feedback loops, you always have one decreasing and one increasing, because that means the overall open loop gain will be negative and you'll have negative feedback. So with this problem, you're going to have to use the numerical methods again, because I don't think on this problem 17 you can solve it analytically, so you'll have to use numerical, whereas this one should be able to solve using quadratic equation. And then finally, problem 18. I'll try to squeeze it in here. Is another feedback loop talking about calcium in our bones. So our bones contain a lot of calcium. If our blood calcium gets too low, calcium will begin to seep out of our bones into the bloodstream to make up for calcium. If the calcium gets too high, your body begins to take calcium out of your bloodstream and store it in the bones. So you're going to have a situation where you have calcium over, and this is going to be the reabsorption rate into the bones, and it's going to go up as you tend to. Actually, this is reabsorption from the bones. So if you start having calcium coming out of the bones, which is really what this is, you get a calcium increase, you're going to increase in the blood. But your body controls this. I don't know if that's an S or an R, but it's a symbol. That controls the amount of calcium coming out of the bones to cause it to have less if your calcium increases. And that's a feedback loop. This is a particularly easy feedback loop because these are linear equations. So you should be able to solve this one very easily using analytical methods. All right, so your homework that's due on December 6th has 4 problems that are feedback problems. They may ask you for set points. They may ask you for how much it changes with and without feedback. They may even ask you for changes in time constants. There'll be all the stuff we talked about today. And then 40, 41, 42, 43 are going to be all about the nonlinear dynamics and chaos with cardiac restitution that we talked about 2 class periods ago. And that is feedback. We're going to talk a little bit more about feedback on Monday of next week. But most of what we need to know, we talked about today. Okay. Are there any questions at all about feedback and feedback loops? It's a very important topic in biology. Your body is basically a bunch of feedback loops that maintains your internal systems at a constant level. So there's literally dozens that you could choose from. Okay. In that case, I will see you Wednesday. We'll have some fun, then you go have a good Thanksgiving, and then we'll come back next week and really focus on getting ready for the conference.